Welcome to page 2 of the example of using integration to solve for indeterminate structures reactions. This page is going to go through turning the moments into rotations, equations, and beginning to use the boundary condition that the rotation of B, well, it's got to be the rotation of B. It follows part 1. We said that because the moment has to have continuity at point B, the moment at point B is the moment at point B. We don't have any point loads, point moments applied at point B or fixed ends. That means that when we put 6 feet in to this, we're going to end up with what we get when we put 0 in for this. And given that we've got only one constant integration to work with, that's pretty good. So putting 6 feet in for this first equation, we end up with moment from A to B, 6 feet. It's going to be negative 6 feet squared kip per 2 feet plus AY times 6 feet. Let's all remember that AY is constant, right? It looks like a variable. We'll solve for that later. So we can pop that in. That's got to equal the moment from B to C, plugging into 0 for x2. Yet another reason to restart your x-axis. This makes it a whole lot easier to do this because, well, 0 squared, still 0. Yada, 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 times 0 is 0. So we just solved for our second constant of integration. And I mean, simplifying it, I guess we can get it down to negative 18 kip feet plus 6 times AY. But there's no simplifying it beyond that just yet. Okay, so now we've got that solved. We've got our 2 moment equations. But that's not enough. We still don't know what AY is, and we still don't know what, BY and CY are. So let's continue integrating and determine our rotations. All right, so the rotation function from A to B, that's going to be a function of x1, and that's going to be 1 over the Young's moduli and the second moment of inertia times the integral of the moment function from A to B of x1 with respect to x. For this one, that's pretty easy, right? That's going to be 1 for E. We don't need to worry about this too much, right? It's a constant, so integral of negative x1 squared over 2, and then I'm just going to put the units out there for this time. I think that's going to help. Plus AY times x1, which is going to end up giving us negative x1 cubed over 6. Still have that unit kip per feet times this, of course, is all in feet. So these are feet to the fourth or third. Plus ay times x1 squared, divide that one by 2, plus some constant integration, c3. Now, unlike the moment that we had from A to B, we don't know anything about what the rotation is when x is 0 or when x is 6. I mean, I guess, sure. Technically, we can look at this and say, oh, it's symmetric, and if it's symmetric, then the rotation at B, where x is 6, has to be 0. But let's not do that this time. Just because. Okay. Now, let's look at the other rotation. The rotation from B to C. That's going to be a function of x2. And that's going to be equal to 1 over EI. Oh, hey, look at that. I forgot that up here. I'm going to go ahead and put C3 inside the parentheses for this one. I think it'll make the number a lot easier to deal with. This is going to be the integral of the moment function from B to C. It's going to be a function of x2. And I'm not even going to try to fit it up here, right? So that's going to be 1 EI times the integral of this right here, negative x2 squared over 2 feet. There's a kip up there. Plus the reaction at A in the y direction, plus the reaction at B in the y direction, minus 6 kips times x2, what time is it, squared, divide that by 2, plus our constant of integration, which we said was negative 18 kip feet plus 6 feet times AY. No, don't integrate that yet. We're not integrating yet. Never mind. That's this step. So that's going to be 1 over EI. Going to use the brackets for this one. Negative x2 cubed. That's going to become 6 feet. Keep that kip. Plus the thing that I already wrote, and I shouldn't have, AY plus BY minus 6 kips times divided by 2. Trying to keep it descending, the polynomial. Plus negative 18 kip feet plus 6 feet times AY times x2 plus some constant integration C. What are we on? 4, I guess. Now again, we don't know what the rotation is at point C, at the end of this. But we do kind of know what the rotation is at point B, which is to say that the rotation at point B is equal to the rotation at point B. So we can do the same thing we did up here to determine our constant integration C2, down here to determine our constant integration C4. Right, we're just gonna say that the rotation of 6 feet is equal to the rotation at 0, which in this case, that's just going to be C4. Let's continue on the next page to do that.